This is section 8.7. So what we'll be talking about this time is what's called hydroboration oxidation. This is some very clever chemistry that won someone the Nobel Prize that tackles a problem that maybe you haven't thought about yet, because we've learned a lot of ways to do additions in a manner that is a Markovnikov addition, but we haven't learned any ways to do an addition that is an anti-Markovnikov. And in this case, these clever chemists found that if you react an alkene with borane, trihydroborane, THF, meaning the dot means the THF is somehow bound to the borane, but it's not like it's not a covalent bond. It is a dative bond. So this is called a THF adduct. When you see the little dot, it means the THF is an adduct. It's kind of like a barnacle on a ship. You know, it's there, but the THF can go on, come off as it pleases. So if you react the alkene with BH3, THF, and then after that, hydrogen peroxide and sodium hydroxide together in water, you get the anti-Markovnikov alcohol. And this is amazing. This was fantastic chemistry that was a huge leap ahead of what people were using before, because as you saw, we didn't have any ways to make anti-Markovnikov products. So the mechanism for this is a very nice one. It's a little bit involved, but essentially it looks like this. So first, let's start with the alkene attacking the boron atom. This is the boron THF adduct here. You see that THF is kind of attached to the boron, but not really. And sometimes you see a negative charge here on the boron for the THF boron complex, but the negative makes it confusing because the boron is super electronegative, even though it has a negative charge, or not electronegative, electrophilic. So I left the negative charge here off on purpose. Now, when the alkene attacks the boron atom, right at the same time, you have attack of a hydride onto the carbocation that is forming. So what happens is, in a concerted one-step fashion, you have this alkyl boron complex that's made. And if you notice, this is still a boron with two hydrogens, just like we had over here. So you can do the reaction 2 more times. And we call this hydroboration because we added a boron and a hydrogen across the double bond. So once you have your trialkyl boron molecule here, you can then perform the oxidation portion of the hydroboration oxidation reaction. And for the oxidation portion, we start with the sodium or the hydrogen peroxide and sodium hydroxide. And the sodium hydroxide deprotonates the sodium peroxide because of pKa differences. The pKa of water is much higher than the pKa of this sodium hydroxide, and because of that, you have formation of this negatively charged peroxide anion. And peroxide is super nucleophilic, especially in basic conditions. And so because of that, you get this attack onto the trialkyl boron that we just made before. Here, R is standing in for our alkyl group because it's a lot easier. So after you have attack, then what happens is that the peroxide substituted boron molecule is not very stable. In fact, it's so unstable that the OH becomes a good leaving group. This is very abnormal. Normally, OH is a bad leaving group. But because the conditions are very basic and this is such an unstable molecule, you have the OH leaving at the same time the alkyl group is rearranging and shifting onto the other oxygen of the peroxide, leaving you with this alkoxy borate molecule plus the OH that you had before. So you repeat this 2 times again, because there are 3, to give you this trialkoxy borate molecule. And once you formed this, this can be attacked by OH that we were forming in the previous part of the reaction. So when OH attacks it, now you have this negatively charged trialkyl borate molecule. And from here, this is also very unstable. But now the alkoxy group that we just formed in the previous step just leaves. It's had enough, it's done. And it's replaced instead by the hydroxide. This repeats 2 more times, and you're left with, once again, your alkoxy group that can be reprotonated from water to give you the anti-Markovnikov alcohol as we wanted the whole time. And this molecule, or this reaction, for the first time in Chapter 8, does have some stereospecificity in its reaction profile. And that's because of that first step. Remember, the first step was a 1-step addition of boron of the boron and the hydrogen to the alkene. And the reason why it's stereospecific is because the alkene has both a top face and a bottom face. And depending on how the BH3-THF lines up, both will go to the same face. So in this case, you have syn, meaning same face, addition across the alkene. But there's no real, there's no advantage, or not advantage, there's equal probability for one face to have this reaction occur as the other. So you will have both faces, both syn addition products in the reaction mixture, but you will only have syn addition products in the reaction mixture. Alkenes are not the only molecules that undergo hydroboration. In fact, alkynes undergo hydroboration too. And alkyne hydroboration is covered in page 419 and 420 of your book in Chapter 9. If you take an alkyne and you submit it to the exact same conditions, BH3 and THF and hydrogen peroxide and sodium hydroxide, what you end up getting is the anti-Markovnikov ketone, or in this case, the aldehyde of the reaction. Remember, if you had alkyne hydration, you generated the Markovnikov double bonded oxygen. But in this case, it's an anti-Markovnikov double bonded oxygen. And the reason why is because the intermediate step is an enol. And enols, if you remember from 8.6, undergo tautomerization to C double bonded oxygens. So this is a way to think about having anti-Markovnikov hydration of an alkyne, whereas previously it took mercury catalysis to give Markovnikov hydration of an alkyne. So this has been section 8.7 and anti-Markovnikov alkyne hydration, or hydroboration of an alkyne.